Dear students, welcome to the EPG Pathshala. I am Dr. Rajkishore Sharma, an Associate Professor in Chemistry Department of Delhi University. Today we are going to discuss about the module X-ray photoelectron spectroscopy. In this module we will discuss the instrumental part, how the instrumentation is used, instruments are assembled for photoelectron spectroscopic technique. This is under the paper of surface analytical technique 2. Outline of the topic that we are going to discuss today. Number one is the main part of XPS, main parts of X-ray photoelectron spectrometer. Then we will discuss about X-ray sources. Then we will discuss about vacuum systems. Then we will discuss electron energy analyzer. We will discuss about different modes of CHA. Then we will discuss about transfer lenses. We will talk about ion guns also. Side views of XPS will also be discussed, and we will discuss how XPS works. To understand X-ray photoelectron spectroscopy clearly, we need to know about the instrumental part of XPS technique. The main part of the instrument are the primary source of X-rays, a specimen on sample holder, an electron energy analyzer, a detector, and an auxiliary ion gun, and a vacuum chamber also, because all these parts are contained in vacuum chamber. The figure shows general arrangement of X-ray photoelectron spectroscopy instrument. Now we will talk about sample introduction chamber. The sample, basically a powder or a pellet, will be introduced through a chamber that is in contact with the outside environment. It will be closed and pumped to low vacuum. After the first chamber is at low vacuum, the sample will be introduced into the second chamber, in which a UHV or ultra high vacuum environment exists. Now about X-ray sources. Natural line width of the X-ray spectrum and requirement of photon energy are two important factors which help to decide the anode material for X-ray source. There must be high enough energy to eject electrons from all elements of periodic table. This is except very lightest element. But line width should not be large, because big line width broaden the spectrum excessively. Most common and widely used X-ray source anodes are magnesium and aluminium, which provide K alpha energy as 1235.6 and 1486.6 electron volt respectively, due to their small line width, about less than 1 electron volt. Both are usually supplied in a single X-ray gun. Such twin anode assembly are very useful because they are able to differentiate between OJ and photoelectron transitions, as well as provide modest depth profiling capability. From the figure, it can be seen that on switching X-ray source from magnesium K alpha to aluminium K alpha, peak position of OJ transition will change on a binding energy scale. This is the main reason that why XPS uses binding energy scale instead of kinetic energy scale. Now we will talk about X-ray sources. As you know that there are different types of X-ray sources, such as conventional X-ray source, monochromatic X-ray source, synchrotron X-ray source, and small spot X-ray source. The most common among these is X-ray source, such as conventional X-ray source, and it is used in XPS equipped with magnesium or aluminium anodes, often as a twin anode for alternative use. The characteristic Mg K alpha radiation at 1253.6 electron volt and aluminium K alpha radiation at 1486.6 electron volt, 1486 electron volt for aluminium K alpha and 1253.6 electron volt for magnesium K alpha, possesses sufficiently high energies for core level excitation as well as a sufficiently low line width, that is below 1 electron volt, to yield XPS spectra with fairly good resolution. The purpose of an X-ray monochromator is to produce a narrow X-ray line by using diffraction in a crystal lattice. Powerful synchrotron electron accelerators have become an efficient photon source for all kinds of X-ray applications, notably photoelectron studies, while conventional XPS usually analyzes an area of several square millimeter. The typical analyzed area of high spatial resolution XPS is of the order of 100 micrometer and below. There exists a number of reasons for choosing to use an X-ray monochromator on an XPS spectrometer. The primary reason for using monochromated radiation is the reduction in X-ray line width. Narrower X-ray line width results in narrower XPS peak and consequently better chemical state information. Number 2, unwanted portions of the X-ray spectrum, that is satellite peaks and the Bresstum-Hulung continuum, are also removed. Number 3, for maximum sensitivity, a twin anode X-ray source is usually positioned as close to the sample as possible. The sample is therefore exposed to the radiant heat from the source region, which could damage or alter the surface of delicate samples. When a monochromator is used, this heat source is removed from the sample and thermally induced damage is avoided. Point number 4, it is possible to focus X-rays into a small spot using the monochromator. This means that small area XPS can be conducted with high sensitivity. Point 5, use of a focusing monochromator means that only the area of the specimen being analyzed is exposed to X-rays. Thus, a number of samples may be loaded into the spectrometer without the risk of X-ray damaging sample while they await analysis. Similarly, multi-point analysis can be performed on the same delicate samples. Why synchrotron X-ray source is more attractive than conventional X-ray source? It is an important question, and here is the answer. There are two main features that make synchrotron XPS very attractive as compared to conventional X-ray sources. A, the extremely high brightness of the excitation, and B, the tunable photon energy. The high brightness, as synchrotron has more than 3 orders of magnitude higher than conventional source, allows application of extremely high energy resolution that is precluded in conventional XPS because of the trade-off between resolution and transmission. The high photon flux also enhances photoelectron diffraction measurements. By tuning the photon energy, the kinetic energy, and in turn the information depth of the photoelectrons can be varied. For example, the photon energy can be selected to result in the photoelectrons of interest having a kinetic energy near 50 electron volt. The energy for which the attenuation length is at the minimum of about 1 to 2 monolayers. Now, XPS requirement from X-ray source. The requirement is it should be a stable vacuum. There should be a stable coolant flow, at least 10 minutes of ideal cycle before XPS experiment, stable filament current and accelerating voltage, avoid long time previously used electron target zone, always use the most possible soft power mode for X-ray source. Avoid X-ray source intensity decrease and or distortion due to improper monochromatization. This in case if hand tuning is available while using different X-ray sources, that is aluminum, magnesium, zirconium, etc. Ultra high vacuum or UHV is required in XPS. That is, the vacuum must be in the range of 10 to the power minus 6 to 10 to the power minus 9 Pascal or 10 to the power minus 8 to 10 to the power minus 11 torr. If vacuum is less than 10 to the power minus 11 torr, then extreme high vacuum term is used. High vacuum in XPS helps to remove contamination and prevents chemical reactions, and it also helps to increase the mean free path of electron, ions and photons, because electrons scatter on gas molecule in the path from sample to analyzer. The mean free path is the average distance traveled by a moving particle such as an atom, a molecule, a photon between successive collisions, which modify its direction or energy or other particle properties. Now about the vacuum system. Mean free path. We represent this by capital L subscript collision COLL between two molecular collisions can be calculated using the formula L collision is equal to KT divided by 1414 P sigma collision, where K is the Boltzmann constant, T is absolute temperature in Kelvin, P is equal to pressure in Pascal, cross section area for collision in meter square, that is pi d square by 4, where d is the molecular diameter. At a pressure of 5 into 10 to the power minus 5 torr, mean free path for air at 20 degrees C is about 2 meter, and therefore sufficient to meet the above condition. If the pressure of vacuum system is about 10 to the power minus 6 torr, then monolayer formation time will be around 1 second, which is unsupportable in surface analysis because a contamination monolayer reduces the signal of the underlying source, and this time period is very short compared to the required for a typical specimen acquisition. Monolayer formation time is in seconds and about 1.7 into 10 to the power minus 6 Pascal, 1.7 into 10 to the power minus 6 upon P torr. The partial pressure of relative gas such as carbon monoxide, oxygen, water should be less than 10 to the power minus 10 torr to ensure negligible contamination within the measurement time. That's why we need UHV, ultra high vacuum environment, during XPS surface analysis. Now a big question, why ultra high vacuum is required? Ultra high vacuum is of the order of 10 to the power minus torr pressure, 10 to the power minus 11 torr pressure. It removes absorbed gases from the sample surface. It eliminates adsorption of contaminants on the sample surface. It prevents arcing and high voltage breakdown, etc. It increases the mean free path of electrons, ions and photons. Now about electron energy analyzer. Electron energy analyzer is the important part of electron spectrometer. Only electrostatic analyzers are used in commercial electron spectroscopic instruments. There are different types of energy analyzers such as the retarding field analyzer or RFA, the concentric hemispherical analyzer or CHA, and the Cylindrical Mirror Analyzer. CHA is also called Hemispherical Analyzer. RFA is most simple energy analyzer, which was firstly successfully applied by Frank and Hertz on the detection of ionization potentials in 1925. XPS is completely performed with CHA type analyzers. RES with radius R1, which is radius of inner hemisphere, and R2 is the radius of the outer hemisphere. The given equation should be followed by the electron from entrance to exit. The CHA consists of two concentric hemispheres with radius R1. R1 is radius of inner hemisphere and R2 is the radius of outer hemisphere. The more negative potential V2 is put on outer sphere is against the inner hemisphere minus V1. The condition that has to be fulfilled when an electron with energy E0 traveling from entrance to exit. If the energy of the electron is higher than E0, then electrons will follow a path whose radius is larger than the mean radius of the analyzer, and electrons with lower kinetic energy will follow a path with smaller radius, and the mean radius is average of the both radius, that is R0 is equal to R1 plus R2 divided by 2. As the above expression, energy of the electrons does not differ too greatly. At the output, plain numbers of detector are provided because electrons will reach at the output plane of the analyzer. Different energies electrons are collected by each of the detector. These detectors collect electrons by adding the signal into the appropriate energy channel. If the size of all detectors is same, the sensitivity of the instrument can be increased by the factor of the number of detectors. Now, different modes of CHA. CHA spectrometer can work in two different modes, that is constant or fixed analyzer transmission CAT or FAT, and constant or fixed retard ratio CRR or FRR. In XPS, FAT mode is used exclusively. The paramount importance using FAT is the spectral resolution. Figure shows the effect of pass energy on resolution and sensitivity. By increasing the pass energy, resolution of XPS spectra is increasing. Now, different modes of CHA. FAT is attained by applying a fixed voltage across the hemisphere that allows electrons of a particular energy or the pass energy between them. In FAT mode, the main job is to transfer lens system which retard the given kinetic energy channel. The pass energy is the given energy that remain constant across the scan of electrons binding energy to allow electrons, that is, electrons with low or high energy will not transmit it. Now about energy analyzer. There are two types of energy analyzer. Number one, hemispherical analyzer, and number two is the cylindrical type analyzer. In XPS, the HA or hemispherical analyzer is most commonly used. The reason is adequate brilliance within the different electron energy range, and there is no binding energy position distortion, that is high precision. Now let's talk about comparison between hemispherical and cylindrical types of analyzers. In hemispherical, resolution is 0.8 to 1 volt, while in cylindrical greater than 1.4 volt. In hemispherical, transmission is high, and in cylindrical it is higher. Luminosity in hemispherical is high with respect to lenses. Energetic position in hemispherical is independent, while in cylindrical it is dependent. For angular dependence, measurement hemispherical is suitable. For hemispherical machining of high precision is required compared to cylindrical. Now about XPS requirement from hemispherical energy analyzer. XPS requirement from energy analyzer: the lower pass energy, that is E0, usually the better resolution of XPS, but improper values of pass energy and input-output slits results in spectrum shape distortion. Made test XPS recording for well-known material and verify the obtained spectral parameter with published data. Now about the transfer lenses. The performance of a HSA is strongly dependent upon the nature and quality of the transfer lens or lenses between the sample and the entrance of the analyzer. The presence of a transfer lens moves the analyzer away from the analysis position, allowing other components of the spectrometer to be placed closer to the sample. It maximizes the collection angle to ensure high transmission and sensitivity. It retards the electrons prior to their injection into the analyzer. It determines and controls the area of the sample from which electrons are collected, allowing small area XPS measurements to be made. It controls the acceptance angle. This has obvious applications in defining the angular resolution for angle resolved XPS, and it is also important for small area and imaging XPS because the angular acceptance will determine the spatial resolution as well as the transmission. Now about ion gun. Ion gun is not the primary excitation source in XPS, but it is used for large area specimen cleaning, and it provides a means of compositional depth profiling in the surface analysis. Generally, construction of ion guns is quite simple. There are several types of ion guns such as plasma discharge with cold cathode, electron impact, duplasmatron, and broad beam guns, and so on. Electron impact source are very popular instead of duplasmatron due to their low cost and compact design for depth profiling in XPS. In electron impact source, electrons are accelerated from hot filament into the cylindrical grid where they collide with gas atoms and forms ions. These ions are extracted from ionization region, and kinetic energy of ions is controllable by the magnitude of the potential applied to the grid up to 5 kV. The duplasmatron is an ion source in which a cathode filament emits electrons into a vacuum chamber. A gas such as argon is introduced in very small quantities into the gas chamber, where it becomes charged or ionized through interactions with the free electron from the cathode, forming a plasma. The plasma is then accelerated through a series of at least 2 highly charged grids and becomes an ion beam, moving at fairly high speed from the aperture of the device. Duplasmatron design of ion source is sometimes preferred to remove materials and etching of large areas rapidly. The efficiency of ion gun depends on many parameters such as used gas pressure, filament current intensity, and etched surface. The ion beam is extracted from dense plasma which produces a magnetically constructed arc. The ion beam is focused and rastered over the specimen by a set of deflector plates. A credit of high etching rates can be given to the source due to achieving high current density. These sources are available in a range of spot size varying from 2 to 2 mm to 5 micrometer. Small size 2 mm ion source provide 80 microampere ion current with a field of view of approximately 15 mm. 15 mm, which is better than 5 micrometer because 5 microampere ion current and a 2 mm field of view. Small size 2 mm ion source are ideal for large area depth profiling in non-monochromatic XPS, and 5 micrometer ion source find as a primary source in the ion beam analysis of materials. Slide shows a side view of XPS where position of the parts of XPS can be seen. Here you can see that the sample will be introduced through a chamber that is in contact with the outside environment. It will be closed and pumped to low vacuum. After the first chamber, which is at low vacuum, sample will be introduced into the second chamber in which a UHV environment exists. Now about energy resolution. A number of factors influence the energy resolution achieved within a spectrum. The diameter of the analyzer, the pass energy, and the spread of energies in X-ray source play a major role in determining the full width half maximum FWHM for a given photoelectric line. Sample dependent considerations are also important, where localized charging may broaden lines regardless of the precision built into the instrument, and therefore effective charge neutralization is an important part of any system resolution. Achromatic X-ray gun relies on narrow resonance peaks in the X-ray spectrum for the anode material and limits the energy resolution possible for a photoelectric line. Monochromatic X-ray source provide improved energy resolution by filtering a narrower band of X-rays from the resonance peak, and this is achieved by exploiting a quirk of nature. X-ray diffraction through a quartz crystal allows only certain wavelengths to be reinforced into a spot, and so monochromatic X-ray can be directed at a sample. The crystal spacing is such that X-ray wavelengths that are multiples of aluminum K alpha X-ray resonance are reinforced by virtue of the Bragg relationship for X-ray diffraction. The fact that multiplies of this wavelength are reinforced by the quartz crystal means that other anode material are possible source for monochromatic X-rays, such as silver or chromium. Commercial X-ray monochromators have offered using both AG that is 2 and 4 chromium K beta times the wavelength of aluminum X-ray line. Now about small area analyzer. The small area analyzer, electrons are dispersed through the hemispherical analyzer so that different energy electrons arrived at different positions in the radial direction. Further, they are also specially dispersed around the circumference of the sphere. The relationship has been exploited by Cintia ESCA 300 and SPEC's delay line detector system, where images can be recorded that show both energy dispersion and spatial information in the form of sets of line scans. VG-ESCA Labs 220i instruments are 220 instruments use additional lenses at the entrance slit and before an imaging detector, which perform a Fourier transform and the inverse operation to allow the energy resolved stigmatic image to be recorded through a hemispherical analyzer whilst operating the deflection mode. Spatially resolved images can also be recorded by restricting the field of view for the transfer lens systems using a combination of magnetic and electrostatic lenses plus apertures, and then scanning the field of viewing using deflection plates. Stigmatic energy resolved images are acquired through the mirror hemispherical analyzer and offer a fast XPS image acquisition mode. An alternative means of acquiring XPS image is to restrict the X-ray source and raster the small spot of X-rays over the sample. This probe-oriented method is used by physical electronics in their quantum range of instruments where the monochromator is used to produce a small spot of X-rays. The X-rays are rested over the sample by scanning a focus electron gun across the X-ray anode material whilst compensating for any changes in photon energy through the control system. How does XPS works? So now we will discuss how XPS works. X-ray source is used to eject core shell electrons. The meaning of core shell electron is that they are very close to the nucleus of an atom, and if we consider electron near to the Fermi level, then exact information about the atom cannot be detected because electrons near to the Fermi level exist far from the nucleus and moving in different direction all over the space. X-ray photons penetrate about a micrometer of the sample but contain information only about 1 to 10 nanometer of the sample. The kinetic energy of the photoelectron is measured by Analyser. During sample analysis, ultra-high vacuum is required to remove excessive charge contamination. The spectrum is plotted between intensity and binding energy of the computer. The spectrum is plotted between intensity and binding energy by the computer. Binding energies can be determined from the peak position, and what type of elements present in the sample can be determined. We can conclude the instrumental part of XPS. We discussed main parts of XPS such as X-ray source, vacuum system, and electron energy analyzer. By using different X-ray source, we can differentiate between OJ and photoelectron transitions. We saw that by charging the X-ray source and position of OJ peak is changed on a binding energy scale. High vacuum is required to remove contamination and prevents chemical reactions. XPS is completely performed with CHA type analyzers. Ion gun is not the primary excitation source in XPS, and it is used for large area specimen cleaning, and it provides a means of compositional depth profiling in surface analysis. Thank you.